Welcome again to the Picture Language Seminar. As you can see, we have a number of interesting upcoming talks. Next week, Chengkai Wang. After that, Xun Gao, who's at Harvard, Joost Slingerland in Maynooth, and Sebastian Palku and Tsinghua, and so on. Today, we're really happy to have David Evans. David is expert on quantum symmetries, knot theory, has a very interesting book on quantum symmetries and operator algebras with Yasu Kawashigashi. And he will talk today about K-theory of operator algebras, orbifolds, and conformal field theory. So David, share your screen. While you're doing that, I should say that David said he'd be happy to be interrupted. So if you unmute yourself by pressing the space bar, you can ask questions.
Okay, so I'd like to dedicate this talk to the memory of our friend and colleague Vaughan, because much of this is based on subfactor theory. So if I'm going to talk about the Verlinde ring through the prisms of, on the one hand, subfactor theory down here and K-theory. So this involves the issue of trying to go beyond thinking of the Verlinde ring as just the representation theory of loop groups and similar classical objects, but trying to find more exotic conformal field theories from structures like the Haagerup subfactor. And one of the key ideas, at least for me, is this notion of Orbifold, which I want to emphasize throughout. So I'll start with a quick summary of subfactor theory. So the simplest example is just to take a finite group G, and if it acts outerly on a reasonable von Neumann algebra, you can recover the group from the inclusion of the fixed point algebra in the larger algebra. And this led Vaughan to vastly generalize the notion of a symmetry to a subfactor, the position or embedding of one factor in another. And some of the data or combinatorics encoded in this inclusion can be looked at as follows. Now, typically, the two algebras are isomorphic, say two 1 factors or two 3 1 factors, hyperfinite. And so you can take an isomorphism of the bigger algebra onto the smaller algebra. And under reasonable conditions, there's a dual object, just as for group elements and group dual objects, such that the composition in this either order contains the identity. So if you take these two isomorphisms or endomorphisms and compose them in all possible orders, then you have endomorphisms between n and n and n and m and so on, but only 4 different kinds. And if you decompose these into irreducibles, and suppose you're in the situation where only finitely many occur, that's the rational case, then you have graphs like this appearing. So say the first column here is n to n endomorphisms. The final column is m to m endomorphisms or sectors. And in between you've got n to m and m to n and so on. So this is the kind of graph that you'd get if the group, the simplest case, is the symmetric group on 3 elements. So there are 6 objects here from the group elements and 3 from the dual irreducibles. And so in this case, this is actually the MM, and this is the NN system. And then there's this NM object in the middle. So over here, this is an example of a subfactor of index less than 4. The index in this language is just the norm of the incidence matrix. So this has to do with the classification of index less than 4. And there's an infinite series coming from, basically from SU2. So in this language, these are the bottom row is the NM system, and these are the NM system. So in this setting, I only multiply the ones at the bottom. So this is not quite the Verlinde ring, but at least I can think about orbifolds here, but by flipping the diagram, this symmetry preserves all the structure of the subfactor, like 6J symbols and so on. So it induces, by taking simultaneous fixed point algebras, you get another subfactor. And to get a fixed point, which is the only really interesting case, that I need an odd number of elements for my A Dynkin diagram. And in fact, to get something new, I have to have an odd number of the form 4n plus 1. In that case, I get this orbifold graph, this D with an even number of vertices. If I have an odd number of vertices, that does not appear as the graph of a subfactor. That appears in another setting. Okay, so I just want to emphasize, in this setting, I can only multiply the even part. So that's not the Verlinde ring. So the Verlinde ring looks something like this, at least for SU2. So this is the representations of the loop group of SU2 at level K. And in that case, I take the representation ring for SU2, but I kill it at a certain point. So Z rho is the representation ring of SU2 generated by this first vertex here representing rho. And then I kill it off at this point here, which is really, in terms of this Chebyshev polynomials, all the other irreducibles can be written in terms of rho using Chebyshev. So similarly for SU3, the Verlinde ring would be in terms of two variables, the first two ones here. So with a notion of Chebyshev in two variables, you take the representation ring for SU3 and then either kill off by the ones here, the ones that appear here, or I can just take the first two along here, and that will also give me the correct ideal to divide out by and get the true Verlinde ring. So for the Verlinde ring, I want to be able to multiply everything together. So to do that, Wasserman looked at positive energy representations of loop groups, but localized them on an interval I, and I primed is the complementary interval. So I is an interval in the circle, loops from the circle into SUN. And then these gave inclusions of 3-1 factors. And for lambda, the vacuum back here, this is not just an inclusion, it's an identity. And then that gives me a single factor n. Then I can think of these inclusions as being given by an endomorphism of this n, such that this isomorphism, the loop group picture, is given by this inclusion here. So everything can be described in terms of endomorphisms of an algebra n, but now all the vertices are represented by endomorphisms, and so there's a notion of addition, and then all the data of the loop group is encoded in these factors and the endomorphisms. So that leads to the notion of a conformal net of factors, and the representation theory of this conformal net indexed by the subintervals of the circle is then reproducing the Verlinde ring as a category. And so there's then a natural question or issue. If you have an abstract braided system, if you have an abstract braided modular tensor category, can you represent it through a conformal net? In other words, can you find an underlying conformal field theory? So I'm going to look at some examples of that, but just to emphasize the language a bit better. So we're thinking of first of all of the Verlinde ring as the representation theory of loop groups at level K, and you can think of that as modules or representations of a vertex operator algebra, or for us operator algebras in terms of conformal nets of von Neumann algebras. So in this setting, the representation theory of the loop group is a category. You have objects which you can multiply with a trivial object, and there is a notion of a braiding so that you can interchange the order. Now, if you had something like a finite group, the representation theory is also a tensor category, and there's a trivial braiding. But in the case of the loop group, this braiding is highly non-trivial. It's non-degenerate. So the only case where if you do this twice, you get back to what you start with for all lambda is when mu is trivial. So there's a strong notion of non-degeneracy, which is there in the loop group case, but not in the finite group case. So there's a notion then of a tensor category and modular tensor categories where you have this non-degeneracy. And then the question whether you can represent this in terms of some underlying conformal net or vertex operator algebra. So there's two cases I want to focus on, which are closely related. Now, for index 4 and below, that's completely classified by ADE diagrams, and they're affine ADE diagrams at exactly index 4. Now, beyond 4, the first subfactor, which has only a finite number of irreducibles, is at index 5 plus root 13 over 2, which is found by Haagerup. Now, this does not give braided systems. In fact, the systems aren't, at least one of the systems is not even commutative. So to get a commutative and braided system, which is even non-degenerate, one takes a quantum double. So this is a notion which generalizes the quantum double of a finite group, and it goes back to all these people here. So if you have a system of endomorphisms like chi on a single factor n, then the quantum double construction in this von Neumann algebra context is that there exists a subfactor of this product which has a number of nice properties. First of all, if you take this canonical composition, iota is the composition, is the inclusion, iota bar is the conjugate endomorphism. If I compose them in this order, then this natural map is just the diagonal part of chi tensor chi opposite. But more importantly, for this subfactor, if I take the AA system in the sense I described before for subfactors, then that's not just braided, but it's non-degenerately braided, and it's a modular tensor category. So in the case when I'm just having a group acting on n, this recovers the construction of Drinfeld of the quantum double of a finite group. But this is a vast generalization, and it allows us to take doubles of the Haagerup and get non-degenerately braided things. Now, the other example I want to look at is related to these groups here. So as I said, these 6 objects here act on one algebra. This is an endomorphism from, say, the inclusion into the bigger algebra, and this is on the dual algebra. So just as for SU2, you can ask whether you can put all these vertices here as endomorphisms on the same algebra. So that means the vertices are endomorphisms, and the graph is given by multiplication by this one single object down here. So in that language, the top part translates to these fusion rules here. If I multiply mu against this, I get the things at the top, which is summation of the group elements. And mu times a group element brings me down here. And we get something like this. So that's the Tambara-Yamagami category. So I've just written down the fusion rules, but what they showed was that there is a category for these fusion rules. But the category only exists if the group is abelian. So in that case, the top part would be identical as the bottom part. Now, these Tambara-Yamagami categories are commutative, but they're not braided except in the trivial case when I've only got two elements here, which is then mu squared is 1 plus a symmetry, and that's the Ising model. So when we go beyond that, so if we have Q elements here, this is, say, under cyclic group, this is really the Potts model. And as I said, in general, beyond the Ising, this is not braided. But we can get a braided system by taking an orbifold. If we identify a group with its inverse, we then take the orbifold according to this symmetry. I'll do this in more detail later. And then it turns out that at least for an odd number of elements, we get a modular tensor category. So I'm going to put these two things together later, the Haagerup and these Tambara-Yamagami orbifolds. Now, I also want to bring in K-theory to the story. So we have the Verlinde ring of a loop group like SU2. Now, Fried Hopkins Teleman described this through the twisted equivariant K-theory of the group acting on itself by conjugation. So, but by twisted, I mean that I'm looking at bundles of compact operators over G, which is equivariant for the action of G by conjugation. So but by bundles, I mean, locally, these are trivial, but on the overlaps, there is some identification using automorphisms of the algebra upstairs, which is the compact operators. So twisted K-theory certainly plays a role for these compact Lie groups, but it's also there for finite groups. And in that case, the Verlinde ring, the representation theory of the double of the group, is again given by the K group of G on G by conjugation. I want to give some indication of that. So if I have just the K-theory of the space G as a set rather than just a group, this is all about vector spaces over G. So I get one copy of Z for each element in the group. But so this is really G-graded vector spaces, and that's ignoring the group operation on G. But if I throw in the group operation on G, I can start multiplying these vector bundles. And because of group cohomology, I can do that in a non-trivial way. And that brings in 3 co-cycles, and it brings in the notion of twisted K-theory already there. So that's when I focus on this part here, the G as a space. So the G as a group brings in not just vector spaces over the point, but representations. And so this combination here of G on G gives me the representation theory of the double. Now that I can explain that in a subfactor language as follows. If I start off with the inclusion which represents the group, now the quantum double of that inclusion is given by this inclusion of fixed point algebras on the product, where this G sits inside G cross G here through the diagonal embedding. So if you translate the language of endomorphisms on this inclusion, you can do it entirely through, very quickly through bundles. So you end up with bundles on G cross G. So this is going to be the modular system. So it's G cross G, bundles over G cross G, which is equivariant for G on the left diagonally and G on the right diagonally. So this picture, the K-theory of that is exactly what I have up here. And but what's that got to do with conjugation? Well, if I have, say, G acting on the right diagonally, I can kill off the second factor by translation. And then I'm just left with a G action of this one on the first factor. And if you look at it carefully, that just becomes the conjugate action. So this groupoid over here, which describes this Verlinde ring, is really equivalent to this groupoid of G acting on G by conjugation. But the advantage of the picture on the left is that it's easier to manipulate with it and vary the action on the left and on the right using different subgroups. That's a key feature of what Terry Gannon and I have done, which will come out later. Okay, so the Fried Hopkins Teleman picture is about describing the Verlinde ring as the K-theory of this space of sections of a bundle of compacts over the group, which is equivariant. So in other words, it's about finitely generated projective modules over a certain C-star algebra. So Andreas Aaserud and I have looked at a different way of trying to analyze this by instead of using these bundles of compacts, we construct a single C-star algebra associated to the tensor category. So I've written it out here for the Temperley Lieb. So that's the SU2 theory, but it works much more generally with braided C-star tensor categories. So this is my abstract tensor category, which for the purposes of this sheet is just, say, SU2 at level K. And then we construct a C-star algebra BK such that the category is reproduced by certain modules, Hilbert modules for that C-star algebra. So of course, it's very easy to do that at the level of fusion rules, just by having the right K group, which has the right number of dimensions. But the issue is to do this in a categorical way, which reproduces all the data. And then this leads to the possibility of the following, which we haven't worked out yet. This is why I've written it out for Temperley Lieb. Now, you can get the Virasoro algebra by a conformal inclusion like this, and then doing a coset construction. So this suggests that we should take the algebras we had before and look at this inclusion and then try and do a coset construction for this inclusion of C-star algebras. Now, again, this is certainly going to work at the level of fusion because that's just a matter of dimension counting within the K-theory. So the issue is to raise it to the level of the categories. So that's yet to be done. Okay, so another direction.
Can I ask a question here?
Sure.
So, there's also a construction of Wyckoff algebras to realize, any modular tensor category.
Yeah.
So are they related in any way? I assume the algebra is finite dimensional and all the Hilbert modules are also finite dimensional, right?
These C-star BK are infinite dimensional there.
Oh, it's infinite dimensional. So that's very different from, how about the Hilbert modules? Are they also infinite dimensional or finite dimensional?
They would be infinite dimensional, but finite dimensional has modules.
Oh, okay. So the algebra is
finite basis over the module, but over the complex numbers, they would be infinite dimensional.
Oh, okay. I see. Okay. Okay. Thanks.
Zhenghan, identify yourself.
Oh, sorry. This is the Zhenghan Wang, station 2.
Okay. Right. Okay. So where are we now? Okay. So Hopkins Teleman was about bundles of compacts over a group equivariant. So now here's another approach which could lead or should lead to maybe new fusion categories, is instead to look at not just bundles of compacts, but bundles of compacts tensored with some interesting non-trivial C-star algebras. So I'm going to look at this MF infinity, which is an infinite tensor product of matrix algebras. No, so there's a bracket missing there. So this is an infinite tensor product. Now the F is going to play the role of the level. Varying F gives me different levels. So the F is an exponential functor on finite dimensional vector spaces. So it takes plus to tensor. And there's two typical examples. One is where I take the antisymmetric product and then take the largest term in the antisymmetric series. That is basically one-dimensional. So in that case, this F is one-dimensional, and so this thing completely collapses. It's just the complex numbers. So taking this functor, the lambda top, will reproduce the bundles of Hopkins Teleman. But if we take the full symmetric power, then these algebras are non-trivial, and we'll get something new. So I'll be focusing on this lambda star here. And we're going to do it by these groupoids here involving the group SUN and Z, which is the circle with a point removed in order to get some orientation sense. And then there's a natural map from this groupoid, just forgetting the other two terms down to G. And the point will be that this is an equivalence of groupoids, even equivariant groupoids, when G acts on G by conjugation. So just as I had that before for the case of the double of a finite group, I could simplify G on G by conjugation by pulling it back to G cross G with an action on the left and on the right. This is, again, it looks more complicated, but there's actually more freedom to do things in here with G on G. So it's this space here, Cal G, that we use to construct bundles. So I need to say what it looks like over this point GZ1, Z2, and it's just a matter of taking the eigenspaces between Z1 and Z2 for this matrix G. And because I've removed a point on the circle, that there is a notion of orientation. So this makes sense about which points are between which other points. So then we define E to be this, and this gives me a bundle. And there's an action of the infinite tensor product on the left and on the right of this bundle, because it clearly acts on the right. And I can make it act on the left using this factorization here. Now, MF infinity absorbs, that's the infinite tensor product of F of Cn. MF infinity absorbs clearly every matrix of the form M or endomorphism of FCN, but it also absorbs these things here. Just if this was 2 by 2 matrices and each MF was 6 by 6 matrices, then I could factor each 6 by 6 into 2 by 2 and 3 by 3, and then push the 2 by 2 into the 2 by 2 part. So this MF infinity absorbs everything like this. So that means that I can make this infinite tensor product act on the left using this decomposition. So that means that this bundle becomes an MF infinity bimodule. So we're looking at the language of bimodules to get, or correspondences, Morita equivalences, to understand a notion of gluing on overlaps, just as in the classical Fried-Hopkins Teleman situation, where you've got a bundle of compacts. On the overlaps, you look at automorphisms to glue one piece to another. So here we're using bimodules to do that gluing. And so we have these bundles, and then there's a natural notion of a C-star algebra associated to this Cal E. And the stabilized algebra is then the section algebra of these with these locally trivial bundles with these more exotic fibers. So in the case of the Fried-Hopkins Teleman twist, where F is lambda top, this collapses and it's just the usual bundle. So we've computed for, this is joint work with Ulrich Pennig in Cardiff. We've computed the K-theory of these bundle algebras for SU2 and SU3. Now, so the K0 is trivial, K1 is this quotient here. Now, strictly speaking, if you really want to get K0, you should use K homology. If you work with K-theory, then it's K1, which is relevant because of the dimension of SU2. When you go to SU3, it reverses and it's K0 that's relevant. Anyway, the interesting part, the K1 is now a quotient, just as it was for the classical twist, where I had the representation ring of SU2 divided by the ideal generated by a single polynomial. Now, in this case, the RF of SU2 needs to take account of the K-theory or the equivariant K-theory of SU2 on this infinite tensor product algebra, which is this localized algebra involving Z rho, the representation ring of SU2 divided out by F, evaluated, this functor evaluated on this representation, the standard representation. So I've written out this for the full twist. So I have to take this exotic looking numerator and divide out by the denominators. And I've written out explicitly what these denominators look like in the case of low level. Now, the interesting case is when K is odd. So K is 3, 5, and 7. So in that case, it's the case that the localization is not necessary, because this rho plus 2 is automatically invertible in the quotient. So I can forget about the localization in the case when K is odd, and it's just the representation ring of SU2 divided out by certain polynomials. And if we choose our generators carefully, we can get these fusion rules appearing here. So this is for K equals 5, K equals 7, and K equals 9. So there are 2 irreducibles which have these fusion rules, and then 3 irreducibles here, and so on. So this can be read in a number of ways. One is that it's the same fusion ring as the even part of SU2 at odd levels. That's one way to read it. The other way is that these graphs also appear for the conjugate modular invariant for SU3. So I want to emphasize that these computations and these graphs are at the level of fusion rings. We don't understand it at the level of fusion categories. And that becomes clearer when we go to SU3, where these pictures are more obscure. So for SU2, we can do this computation by a Meyer-Vietoris, because we can think of SU2 being parameterized by the maximal torus. So the maximal torus you can split into 2 semicircles overlapping, and then do a Meyer-Vietoris built on that. But for SU3, it gets a bit more intricate, because it isn't 2 overlapping portions of the maximal torus that you need, but 3 of them. So this is the maximal torus for SU3 divided out by the Weyl group. So we need, instead of 2, we need 3 things. So the Meyer-Vietoris gets more intricate, and it has to be replaced with a spectral sequence. So in that case, the computation is trickier, and we could do it in certain cases. So first of all, if I take the full twist, then we could compute the K-theory explicitly for these small values of m, but we had to do it using Mathematica to compute kernels and co-kernels. In the case of working over the rationals Q instead of working over Z, we could do a complete calculation, but it's over Q because at certain points in the calculation, we have to average over finite subgroups, and that involves dividing by integers. So with these provisos, we made these computations for SU3, and in that case, remember the Weyl alcove for SU3 looked something like this. And for the classical twist, I was dividing out either by the polynomials here or for 2 polynomials over here. Now for SU3, there's a similar one, so it's in K0. This is the computation over Q. I take similarly this localized K-theory for the action of SU3 on the infinite tensor product algebra. And then there's an ideal generated by 2 polynomials. In general, they look like this. In the case of the classical twist, of course, it completely collapses to what we know from the description of the fusion rings as ideals, has been given by ideals. So in the case of the full twist, it looks like this. So these, the 2 polynomials I have to use to kill off the representation ring look like that. So in the case of the classical twist, it's only the top term that comes in. And so I have, these are the 2 that come along the bottom boundary. So again, this is at the level of fusion rings. We have not understood this at the level of fusion categories. So we don't know if there are interesting fusion categories arising from these constructions, but there's of course a lot of variables which I haven't thrown in here. These are examples of twists. There are others which may be better choices to get some interesting categories. Right, so, okay, so let's go back to the Haagerup subfactor. So these are the graphs, the two graphs that appear for this first subfactor beyond index 4, which is of rational number of irreducibles. So this graph has a symmetry about this vertex. I have one arm going off here, and then I have two arms going off here. So there's certainly a Z3 symmetry of the top, and maybe even an S3 symmetry. Anyway, the fusion rules of the top 6 are given by this formula here. If I ignored this blue part here, this would exactly be a description of a symmetric group on 3 elements, or a dihedral group. If I take the square root of the index, I get this statistical dimension, and then it's well known that this is a better notion to compute, because it's not just multiplicative, it's additive. So I can replace these formulas by numbers, and we get these quadratic equations, and that leads to this number root 13. So this system is clearly not commutative, so it's not going to be braided. But we take the double, and then we get something like this. So this is what Terry Gannon and I computed as the modular data for the double of the Haagerup. In this case, there are 12 irreducibles. The diagonal is of this form with, as you might guess, 13th roots of unity coming in. And then the S matrix takes this particular nice form. It was computed by Izumi numerically, because that's how these things come about, by constructing these subfactors through Kunz algebras, is through solving certain fairly obscure equations. So we simplified it to this form here, and there's a pattern coming in which goes beyond root 13 to generalizations, in that this part here seems to have something to do with the dihedral group, S3 in this case, and this has something to do with SO13 at level 2, because the modular data for that group looks basically like this. So that suggests that this has something to do with the modular, something to do with gluing together a symmetric group and SO13 level 2. Now, that was our original viewpoint. Now we think of it somewhat differently. With, instead of SO13 level 2, we look at the level rank dual O2 at level 13. So that's basically dihedral and level 13. Okay. So now I'm going to focus on the two components of this Haagerup sub, at least the double of the Haagerup. For that, I'm going to bring in some Potts models. So I'm going to think of a Potts model for a cyclic group with Q elements, where, say, Q is 13. So when Q is 2, this is just the Ising model. We know that there's a transfer matrix formalism which enables one to solve that. using Pauli matrices and the fermion algebra. The generalization of that to the Q-state Potts model, this is in Baxter's book, and basically goes back to Temperley Lieb, is that one has these relations generalizing the Pauli relations. And if we take spectral projections, where we get the Temperley Lieb relations, non-nearest neighbors commute. And then the critical point is that the transfer matrix in this Q-state Potts model decomposes in terms of two matrices involving E odd and E even. And high temperature, low temperature duality involves interchanging V and W, or E odd and E even. Now, if you translate that into operator algebraic language through using this Kunz algebra, you can actually use this formalism, just these lines here, to get an endomorphism on a Kunz algebra, which reproduces exactly the Tambara-Yamagami relations. So you can construct Tambara-Yamagami explicitly from this Potts model. Okay, as I said, this is not braided, but when we take the Orbifold, which in the operator algebra language means taking a cross product or a semi-direct product with the Z2, we end up with these fusion rules here. So when I take this identification, I have to identify alpha G and alpha minus G. So I average with this MG. There's a dual action coming from the dual group, that's sigma plus and sigma minus. Then the original mu, because of this parity thing, I now get two of them, mu plus and mu minus. So it's what I've written here are the irreducibles for the double, for the orbifold of Tambara-Yamagami. And so I've represented it by this picture here. There were originally 13 points on this circle. I identify the top half with the bottom half. So I get 6 red ones, but the fixed point here splits into 2. And then on the right-hand side, I have these 2 twisted fields, which I represent by mu plus, mu minus. But because Q is odd like 13, there's only one fixed point. And so there's only 2 black nodes here. So these fusion rules have this kind of graded Tambara-Yamagami expression here. Okay, so these are now I'd like to use to build up the Haagerup. So instead of using SO13 level 2 and the double of the dihedral group, instead I'm going to take Tambara-Yamagami on Z3 and on Z3 cross Z3 and take their orbifolds. So for Z13, I have exactly what I have before. For Z3 cross Z3, there are 9 objects here. The identity gives me these 2 black nodes here. That leaves 8 elements in the group. I identify half of them with each other, so that leaves just 4. And then there are these 2 twisted fields. So then that's the fusion rules I had before for each of these parts separately. Then remarkably, the fusion rules for the double of the Haagerup now look like this. I had 12 irreducibles for the double of the Haagerup. I have 6 red, which was the bottom right and the bottom part of the matrix related to SO13 level 2. And then there were 4 in the top, plus these 2, which now represent the top 6. And in this language, the 2 black ones are no longer representing Z2 as they were up here, but sigma plus is of course the identity, but sigma minus is now highly non-trivial. When I square it, I get everything in sight. Every irreducible appears. So that's what I could call the regular representation. And then the other fusion rules can be described simply like this. If I multiply a blue by a red, I again get basically everything, except it cannot be quite everything because mu is not the conjugate of m. The blues and the reds are self-conjugate. So that means it's R minus. I have to subtract sigma plus from R. But apart from that, everything appears. So if I multiply two blues, I get the fusion rules which I had before for the Tambara-Yamagami. If I multiply two M's, there's a kind of supersymmetric concept coming in where I don't add them, I have to subtract them. And so that there's this very highly structured formulation of the fusion rules for the double of the Haagerup in terms of these two Tambara-Yamagamis, or at least their orbifolds. So that suggests the first thing to do to understand the double of the Haagerup is to understand better the doubles of Tambara-Yamagami and their orbifolds. So that's what I did here with Terry Gannon. So in the case of, it's this thing at the bottom here, which is the punchline for the previous thing, that these Tambara-Yamagamis can be represented by conformal nets. So that's the least thing I would need for surely for the double of the Haagerup. And similarly for the double, at least, for the double of Tambara-Yamagami, there's again a conformal net. I need odd in this case here because of this issue of if you've got too many fixed points, then it gets intricate and things fall apart. Now, this study also involved some construction results for conformal nets involving finite groups. And in particular, constructing conformal nets associated with doubles of groups, as in the one up here, even with the twists with these three core cycles. And also this, if the representation ring is of this form here, then it's the fixed point algebra under a holomorphic net. And one key tool in all of this up here was actually going back to Vaughan's thesis on the classification of finite group actions on the hyperfinite 2-1 factor, where he had these cohomological exact sequences involving this lambda, which was what he called the standard invariant. And we need to use that in this analysis up here. So that brings me exactly back to where we started with Vaughan's ideas about subfactors generalizing group actions. So I think I'll finish there. So thanks for listening.
Well, thank you very much, David, for a really beautiful talk. I think you left Vaughan smiling down at you, and I think he'll be very happy. So it's amazing how many experts are in the audience. I'm sure there are lots of questions.
Hi, David. This is John Wei.
Hi.
I have a question. First,
Yeah,
thank you very much for this very beautiful talk. And I'm sure one will be very happy to see this work. And my question is, how do you get like versatile algebra from this construction?
I don't know at the moment. That's a problem that rather than a. I have. Can I go back to the? Right, this is yet to be done, but this coset construction here suggests one should look at this inclusion here and try and understand some coset theory for this, because this completely encodes through the modules the SU2 theory.
Yeah.
So it should be there, but I don't know how to dig it out yet.
But maybe I can, this is Zhenghan Wang again, there is a indirect way to see it, right? If you construct this local conformal net, and then we can input, the work of Kawahigashi, Dango, Sept.
Yeah, sure, but
get the VOA, and then you get the versatile algebra.
Yeah, sure, but that's using a sledgehammer.
Yeah, that's a way to see.
I mean, there's always been this problem about trying to get a direct link between Verasoro and Temperley Lieb without going through all that extra structure. That's what I'm really posing here, rather than something independent, just some direct link between this Temperley Lieb picture here and Verasoro.
Another question is, here you are using the bimodules, and how could you interpret the braid? Since like if you want to realize the double Haagerup, you need the braided tensor category. And on the conformal net level, there is a natural way to construct the braid, but here, what would be the natural way to get a braid?
Well, so the braiding comes about from finding a nice map from B tensor B into B at the level of C-star algebras, right? And then that induces a map on modules. It allows them then to multiply modules. And so it involves finding a nice way, a concrete way of going from B tensor B into B, not just at the level of fusion rings, but at the level of categories. And so that's what we did. So in the case of Temperley Lieb, it's purely diagrammatic. You can just draw one diagram and another diagram, then put one on top of the other, and use the braiding so that you can lay one on top of the other. It's a bit more work with these more general categories, but the idea is basically the same.
I'm sorry, I don't see that. Why the map from B tensor B to B give you the braiding?
Well, no, that doesn't give you the braiding. That gives you the how to multiply modules, but it is related to getting from you need to understand if you have B into B, there's two different ways of multiplying into B. So those things have to be compatible. And it's the braiding that relates that.
Hey, hi David. This is Paul Fenley.
Hi.
So let me ask a very lowbrow question. On the slide, I think it's 2 or 3 after this one, when you were talking about the SU2 case, before you did the SU3 case, you had these pictures that
Yeah.
when you were talking about a fusion, yeah, that one. So when you're talking about this fusion ring, I mean, those pictures look like the fusion rules for the spin one, what physicists call the spin one object in SU2K, SU2 level
Yeah,
K.
it's the even part of SU2 for.
Yeah, exactly. Sorry, even, yeah, okay. And so is there an analogous statement then for what you're doing for SU3, where you can say it's a subcategory, you know, it's got somehow some subcategory?
Yeah, I've tried that, but I cannot find it.
Is it, do you think,
the polynomials are more intricate?
I see. Do you think it doesn't exist, or it's just too weird?
It may be that we haven't chosen the right functor.
Okay.
There are generalizations of these functors where you can put in some parameters. Maybe if one chooses them more carefully,
Okay.
well, one gets better. So maybe this choice here is the wrong one. So using these polynomials, I could not see.
I see.
How
There's no sort of obvious Chebyshev kind of thing for.
No.
Oh well. Okay. Good. Thanks.
So are there any other questions? There's so many people in the audience who've worked on related things. Let me ask a silly question. Can you relate this to new exactly soluble models in statistical physics?
Well, I mean, of course, there are these. There are Q-state Potts models and their orbifolds, right? But how to write down a solvable model for Haagerup, I do not know how to do, which builds on those two things. I do not know how to do that. But I believe there should be a solvable statistical mechanical model.
What about a general, and you talked about generalization of Kramers-Wanye duality. Does this give some putative critical theory?
Yeah. So that's this is the system which really describes the critical model. But what I don't know is how to make sense of the gluing of the two components. I'm convinced that there is not just a conformal field theory for the double of the Haagerup, but a solvable statistical mechanical model.
I have a question. How can the Kunst algebras come in when you're looking at 2-1 factors? I mean, it's they're in some sense they're the extreme opposite situation.
Yeah, well, if you really want to use the language of endomorphisms, you'd better work with 3-1 factors rather than 2-1 factors.
Oh, I see.
So Kunst algebras are more natural than.
No.
So that's why one goes from, for the Ising model, instead of looking at 2 to the infinity UHF algebra or the Fermion algebra, one looks at O2. And so endomorphisms in the O2 picture are much cleaner.
Thank you.
I glossed over the fact that what algebra I was really working over. Was it 2-1 or 3-1?
do you always get 3-1 factors in this setting which you're considering, only in this Ising model?
No, in these general settings, these are 3-1. I mean, they naturally appear as 3-1.
Yeah,
But
thank
the
you.
3-1 subfactors typically factorize as an inclusion of 2-1 tensor with a single 3-1.
Yeah, thank you.
But it's more natural to work with 3-1, I think.
So I see Roberto and Yasu are here. Do you have anything that you'd like to say?
No, it's okay for me. I have to.
Werner?
I was going off a tangent, which is probably stupid, but I mean, I was thinking if one could make use of these kind of ideas for the classification of finite simple groups, because Attia always was saying that there must be a much better way than writing 10,000 pages or so. And in particular, this even odd distinction, if one could get an easier proof for the fact that, well, basically there are no finite simple groups of odd order. So, but it's probably stupid. It's just I was going off on I would be surprised if Dias thought in this way, but maybe he has.
I have not thought in that way, but maybe one should look into it. Yeah, definitely. No, I had not thought of that before.
I mean, it's certainly a new way even of looking at groups. You get out much more structure. And
yeah.
Well,
But
David,
here there are some symmetries, right? And it's like with monsters, it would be more difficult, but who knows?
Feng Shui has worked on similar issues, trying to get results on group theory, from subfactor theory, wall conjecture.
I think about the lattice of subgroups, is it? That's. Yeah.
Well, David, thank you again for an absolutely beautiful talk with so many interesting ideas. And we look forward to how it develops. So thank you. See you again next week. Bye-bye.
Yeah.
Bye-bye.